My name is Puneet Jubahanaya, and I'm from the University of Luxembourg. And today I'm going to present a topic on the demand-aware beam design and user scheduling for pre-coded multi-beam GEO satellite systems. It was a nice talk from Dr. Schwartz. It was a good introduction for me to begin with. So, just a second. So, So to brief it as an objective, I would like to first talk about what are demand-driven systems, and Dan will talk about what is system and channel modulation, channel model, which we consider here. And then we talk about what is demand-aware beam design, and then demand-aware user scheduling, and then finally show some results and simulations and conclude it. So to start with, what are demand-driven systems? So as you can see on the figure to the left, you can see that it's a flight or aeronautical user locations at different timestamps of the day. And also we have pictures of, a figure where the ships and maritime user locations at different timestamps of the day. So you can notice that these ships and flights are highly mobile. So they keep moving. So hence the demand distribution is not geostatic, it's mobile. So this is a big problem in satellite industry because it's a recent trend, because as he was talking about, satellites have been mainly used for broadcast services, and now because of broadband services there comes a problem with mobile users. So the major problem if we see here is how do we satisfy the demand of these users who are mobile? So when we have multiple beams, you can see the beams are in the green color there. So these are the fixed beam footprints. How the beams would look on the surface of the Earth. So the beams are static, but the users are moving. So there will be conditions where certain beams are overloaded, or there are some times where certain beams are not utilized. So to avoid that, we are looking for demand-driven solutions. Also, we can look at this particular picture from Dr. Eva. It says it's a normalized traffic profiles of maritime and aeronautical services. Previously, I spoke about how the demand varies geographically, but the demand also varies with time. So a same user has a higher demand at certain point of a day and a low demand at certain other point of a day. So there is to be a need to shift from the objective of system throughput maximization to demand satisfaction. So most of the previous works and current trend is increasing the offered capacity, but now we should look more towards how do we satisfy the user demand and not to provide too much throughput for regions where it is not required. And also for this, it's very important to consider geographical position of these users and also the traffic demands. And this can be achieved by avoiding overloading or underusing of the beams. So demand satisfaction also has to be provided both at beam level and user level. So for which we decided to employ a demand-driven adaptability at multiple levels of the transmission chain. So in this presentation today, I'll be talking about two such places. So before I go to the demand-aware solutions, I want to talk about the system and the channel model. They're pretty basic. We have a satellite gateway, space segment, and also the user location, users here. So we have a high throughput multi-beam satellite systems employing multiple spot beams, which for the provided coverage region. And we also have non-uniform spatially distributed mobile broadband users, which includes aeroplanes, which is ships, and also normal pedestrian users. And then we also have this space segment consisting of programmable payload GEO satellite with array-fed antennas with beam-forming capabilities. And so considering this system model, we introduced adaptability mainly at two regions. One is at the beam designing level, and another one is user scheduling level. So the channel model goes like this. We have for y of n is the received signal, which can be expressed in equation number 1. The model can be expressed as the basic equation y is equal to hx plus n, where your h is the channel matrix, which has both the phase component as well as the basic channel matrix, which depends highly on the receiver antenna gain too, and the transmit antenna gain. And the phase matrix has been, can see that using equation 4, and the X is the transmitted signal, where W is the precoding matrix, and S is the symbols which are the transmit symbols. So the precoding matrix can be computed by using a very popular MMSE precoder, which probably will be seeing in the future presentations too. And we consider equal power distribution among all the beams. So moving on, what is demand-aware beam design? So talking about demand-aware beam design, basically, I would like to start from the scratch. So we had these single beams covering the whole of the United States in the first figure, and then the multi-beam concepts came up, and then you can see multiple spot beams designed. And then the whole idea of our previous works where they're designing circular beams, which is projected on the surface of the Earth. So most of the works thought about how many beams should we have to give a coverage for a certain region. And also you can see in the figure number 3, it is also a fixed design. It's a ESA provided 71 beam footprint. The beams look quite weird because of the curvature of the Earth. You can imagine if a beam is being projected on a globe, how the distortion happens. So what for this particular problem, I mean, for this paper, what we consider is the 6 beams which we take from that 71 beam pattern. So you can see these 6 beam patterns are fixed, and the blue dots you see are the users, and these users are highly mobile. So this is basically a fixed beam design. So fixed beam design actually fails to distribute the broadband traffic demand across all the beams evenly, and it will result either in underuse of the offered throughput or overload the beam capacity. So hence the beam footprint has to be designed such that the occurrence of unbalanced aggregated beam demand is avoided. So this is solved by the problem statement which we define here using a clustering problem, which is very close to set partitioning problem. We are minimizing the weighted Euclidean distance, where R is actually gives the distance between user M and the center of a cluster, that is C of tau k, and then the second part of this equation that under brackets is basically the weights which we add, so that we can also consider the user demands in our problem. So we are minimizing to obtain those clusters, so that the demand is more equally distributed among these clusters. So the constraints include the first one, where we first constraint makes sure that all the users are considered for the consideration, and the second one is actually we make sure that no beams is been left out, or at least one user is considered for one beam. And then the third constraint is basically to make sure that there is no beam which has been scheduled without any user. So if there is a beam, that should be users. And the last one is basically to compute the new centroids. So to solve that particular problem, we use something called Lloyd's iteration partition clustering algorithm. So it goes like this. We first select the cluster centroids, basically using a popular k-means plus algorithm. And then we run this in a while loop. The step 2 will be to compute the R matrix, which is nothing but the distance between the cluster centroids and the user locations using the equation 9. And then the step 3, we assign those users to those clusters which are much closer to them, and this we can find out using the R matrix. And then finally we compute the new cluster centroids using the equation number 10. So we go this in a loop until there's no cluster assignments do not change, or the maximum number of iterations are obtained. And by the end of this algorithm, we would obtain something like different clusters. Each clusters has to be converted now into a beam. So solution looks like something like this. So there you have the fixed beams, which looks very much like a standard static design. Whereas in the adaptive design, based upon the user demand, also on the user locations, we change the shape of the beams. That means we point the beams where there are more users, or we modify the shape and size of the beams based on the number of users and the user demand. So obviously, when we get this in the previous step, we actually got the cluster centroid, so we know where they're pointing. But to give the equal coverage of what it was to compare with the standard, we use something called as Vernon tessellations. That's the red convex polygons you can see there. So obviously convex polygons cannot represent a beam footprint, so we have to approximate it to ellipses for mathematical tractability and topological packing, and hence we have approximated to the green ellipses there. So to make it interesting, put some slide here. It's not the 6 beams here. You can see the 71 beams. That means whenever the users have been changing at different timestamps of the day, the beams are getting adapted to. So you can see that the beam shape's becoming smaller and lesser, or sometimes it's been pointed at different places. So it's more of an adaptive design. So this is one segment where we introduced adaptability. And the second one which we introduced was something called as demand-aware user scheduling. So user scheduling was in satellite industry was popularly dominated, I believe, by like semi-orthogonal scheduling, or sometimes simplistic approaches like random scheduling. But here we use something called as weighted semi-orthogonal scheduling. That means we introduce demand by introducing a factor called alpha of m, where alpha of m is basically, I mean, you can see in the step 1, we first try to give priority for every user by computing alpha of m. And then in the step 2, we initialize this particular tilde as this is a matrix which we use to generate a set of users every time frame. So from t is equal to 1 to t, we compute the first one, that is u1, who maximizes the alpha factor and also has the very good channel. And then in the step 3b, what we do is like we try to find out the next k-1 users. So that's somebody who maximizes I mean, inside that for equation. So you can see inside the summation, that's called something called as cosine similarity. So cosine similarity is nothing but it's very close to, it's an opposite to orthogonality. So if we are scheduling 6 users, if they're as orthogonal as possible, it's nicer because the precoding works better. So hence we also update our priority every t seconds, and so this is run in a loop for user scheduling. So together, we have introduced demand-aware design at 2 levels. One is at beam design level, and another point at user scheduling. And we tried to show some results. So for results, we divided into 4 different cases. That means if we have not at all introduced demand-driven adaptability, then we call it as the case 1. If you have introduced demand-driven adaptability at only user scheduling, then it's a case 2. And if you have introduced adaptability at beam design, it's case 3. And if we have introduced adaptability at both the cases, it's case 4. So the simulation parameters are on the right, and I would straight away go and explain the results. So you can see that the beam level demand satisfaction, it's very, you can see it's very good in terms of case 4, because why case 4 works better in respect to others is because in case 4 we make sure that the total demand of a system is distributed more evenly among all the beams. So that can be shown in the figure on the right. So the fixed design actually has a most uneven demand distribution. So some beams have to really very high demand that has to be met, whereas some beams have very low demand to be met. Whereas while by distributing the total demand more evenly, we are making sure that the demand satisfaction is achieved at the beam level. And at the user level, you can see the green curve, which is the case 4, which outperforms all the other 3 cases. So it's very convenient that to say that using demand-driven adaptability at both user scheduling and beam designing actually performs well. So that's pretty much the end of the presentation today. I'll just conclude with some of my comments. So we introduced the system-driven adaptability at 2 different levels. One is at beam design and at user scheduling. So contrary to the current state-of-the-art solutions, we consider the actual demand requirements at these both 2 phases. And in this work, we show that the benefits in terms of demand satisfaction and at both beam level and user level. And this is a relatively new approach than looking at throughput maximization. I think demand satisfaction is a new approach where we should be looking on. In particular, the conventional systems face unbalanced situations with significant amounts of unmet capacity, while in our case, the user's demand requests and the beam's demand requests have been met quite considerably. So with that, I'm going to end my presentation. So if you have any questions, please feel to ask. Thank you.